Yeah, good afternoon, everybody, and congratulations to all the award winners. I'm happy to introduce Dr. Sandip Kumar Saha. Dr. Saha has joined the Department of Mechanical Engineering at IIT Bombay in 2012 and is presently an associate professor. He received his BE degree in Mechanical Engineering from Jadavpur University, Kolkata. He has pursued MSc as well as a PhD from Indian Institute of Science, Bangalore. Before joining IIT Bombay, he was with the R&D department of Tata Steel as a researcher. He has received BASc fellowship to conduct research on solar thermal applications. His research interests include CFD, heat transfer, thermal management of electronics, microchannel cooling, thermal management of buildings, etc. So he has published over 95 journal articles and filed 6 patents. He is a member of editorial board of Scientific Reports since May 2021. So with this, I welcome Dr. Saha for his talk on packed bed, latent heat thermal energy storage, advancement in the modeling and analysis. Dr. Saha.
Thank you, Professor Seshadri. I hope my presentation is visible to everybody.
Yes, it is.
So, thank you, Professor Atre and Professor Pradeep and jury members for selecting me for this award. Today, I will give presentation on packed bed latent heat thermal energy storage. Although my award application was in the field of solar applications, but mainly I want to save time and I want to talk on the modeling approaches what we adopted in this thermal energy storage. So this packed bed thermal energy storage is not a new storage technology, and this application actually is wide. For example, chemical industry use this packed bed technology for their reactor, as well as mechanical engineers also do some this type of technology to store heat. Now my work is mainly on thermal storage energy, where I will be using some type of material which is known as phase change material to stabilize the temperature of the storage when it is needed, basically. So that's why I will start with the solar energy context. As you know that solar energy is intermittent in nature, and also after sunset the solar energy is not available. So there is a need of some kind of storage, whether it is chemical energy storage, whether it is electrical energy storage, whether other form of energy storage. But here I will only talk about thermal energy storage as the conversion from one form to another form of the energy is not there, so it has a very high efficiency. So also this type of storage is mainly used to store energy at a lower cost, basically. Now here mainly people are using sensible heat storage like gravels, pebbles, very common river bed pebbles to store the energy. However, in my case, I'll be using some phase change based material storage or material based storage to store this energy. Now, why I want to use this material? Because it has very high latent heat compared to any other material, and also the phase change material has very small range of phase change temperature within which it can store the heat. That means the temperature difference between the source and the storage are not needed very high, which is required for storing heat in sensible heat storage. So basically the objective is to reduce the fluctuations in the heat transfer fluid caused because of this intermittent nature of the solar radiation. So this is the application point of view. But when we go to the packed bed type of storage, I will now demonstrate that how we can do some modeling and what are the state of the modeling we have developed in our lab to analyze this storage. So what is the phase change based technique? Simple thing is that this we know from our 7th or 8th standard knowledge, that if you heat one material, something like paraffin, if you heat, so when it reaches the melting temperature, the temperature of that paraffin will stabilize and it will melt from solid to liquid. And once melting is done, then this paraffin, solid paraffin will be converted to liquid paraffin. And if you solidify back, it will follow the same reverse path, basically. and again back to the solidified condition. But the problem with this phase change based material is that it has very low thermal conductivity. And because of this, the heat transfer within this phase change material is very low. And as a result, there will be thermal stratification. That means a localized increase of temperature near the source heat transfer line, basically. So in order to remove this, there are several techniques adopted. One of this is packed bed thermal energy storage, which I will discuss now. So as I told you that I will be mainly concentrating on modeling approaches. So broadly, the modeling approaches adopted to analyze this are, first one is discrete element model, where you individually model the pebbles or the balls inside the thermal energy storage and analyze it using full-fledged fluid flow and heat transfer equation. But another way of doing this thing is porous medium model. Now, in case of discrete element model, the challenge is that it is very computationally expensive because you have to resolve each the pebbles or each balls or encapsulated balls inside this storage. Whereas in porous medium model, you need not to resolve everything. Okay, so in that context, there are few models available, and depending on the assumptions, like whether you want temperature gradient in the solid, means that in the filler material, or you want continuous material in the fish in the storage tank, or if you want to neglect the convection inside this storage, then different model evolves basically. So which is known as concentric dispersion model, continuous solid phase model, and Schumann's model. But if you want to do full-fledged analysis of this storage using porous medium model, then you can write very simplistic equation like continuity equation, momentum equation, as well as the energy equation to analyze this. Now, when we come to analyze this thermal part of this storage, there are two types of model exist. This is already people have used. So one is thermal equilibrium model, where they assume whole packed bed as one fictitious material and assuming everything is at average properties, and they model it simply. But whereas if you assume that the filler material and the heat transfer fluid material has different thermal conductivity as well as properties, you can use some non-equilibrium model and you can actually do the simulations. Now, in order to couple this heat transfer fluid and the capsules which in which these phase change materials are kept, okay, so you need some closure equations, and in order to do that, people have suggested some correlations based on the fluid flow properties like Reynolds number, Prandtl number, and the velocity. However, when we started this work, this module was not available either in OpenFOAM or in ANSYS Fluent. So in 2016, one of my students actually implemented this, and he assumed that the phase change is occurring inside this phase change material, but we neglected there is no fluid flow because of this phase change. So basically, we assume that conduction heat transfer occurring within this phase change material, basically. So he developed that model, and we wrote these equations in the form of UDF and UDS, and from there onwards, actually the trend started to use this kind of equation in, say, either in OpenFOAM or Fluent to model this type of storage. Okay, so now whatever we do in modeling, we need to validate our findings. So that's why we have developed an experimental setup in our lab to find to actually validate our numerical models. Now, this actual experimental setup operates something at a temperature of 200 degrees centigrade, looking into the application of medium temperature solar thermal power plant. Although I am saying solar thermal power plant, but this storage is equally applicable to solar PV type of applications also. Basically, what we are trying to do is that we want to store excess heat in this storage, and when this heat is needed, say during this intermittency of solar radiation or after sunset, say, we can extract heat from this storage and actually run the turbine basically at a constant or at a almost constant power level. And also this storage will enable us to integrate solar thermal power plant or solar PV with the national grid also. So basically this thermal energy storage is basically to actually reduce the gap between the energy demand as well as the energy supply. So this was the intention, and accordingly this experimental setup was developed. So we see that there is, if we do some validation, still we got some deviation from in our numerical predictions. Now there are many various reasons at that time that we got the deviations, which we rectified later gradually. But now thing is that initially we used a spherical type of capsules where phase change material was encapsulated. Now we are using cylindrical type of encapsulations, and where PCM will be or phase change material will be encapsulated. Now when I do modeling, as I told you at the beginning, the model was very simple, and then what we used assumed that the heat transfer within this phase change is conduction. Now we have to relax this, basically means you have already seen that paraffin is melting. That means it is going from solid state to liquid state. That effect has to brought into my model. So in order to do that, what we do is that we use very basic concept in our heat transfer, which is called thermal resistance model, as well as another step is there, which is where we bring the effect of convection in the phase change based in the melting basically of the PCM or phase change material. So using this equation. So once we do this, we have seen that our result is improved with the experiments and with respect to the experiments, and it is predicting better. However, still there is a scope of improvement, which I will discuss later. Now, going into the another model, where basically I want to say why I want to develop this model is that, see, when we run this model in either in open source software or even our in-house code, it has been seen that for a dimension of 800 mm length and the radius of 50 mm, for two-dimensional case, it takes around 6 to 8 hours to simulate only 1 hour of operation. Now, when I will run this model for a solar thermal power plant or solar power plant, which runs, for example, around 20 years to 25 years, means that model cannot be used. Okay, so that's why we want to have some reduced order model, which can be used to predict the performance of the solar thermal power plant for such a long period of time. So that's how our new approach or new model is developed basically. And this model is so flexible that means I can fill whole tank with capsule, filled with phase change material, or partially filled basically. And here I will describe that model, which is basically a base model. And upon depending on the applications, this base model can be actually enhanced. So I will give a very brief idea of this model, where what we do is that we do some energy balancing and you introduce some switching function to develop our model, and then we use some coupler basically or closed form of the equations to arrive at the final equations. But one thing you understand here is that here we have neglected the fluid flow part completely. But if I neglect fluid flow part, that means I have to bring its effect through some terms. Okay, otherwise, if I just solve only one equation instead of 3 equations, it will not give me exact or it will not give me very good actually result. So that's how we now bring out the physics through several terms, which will give me the effect of fluid flow in these equations. So once I do this, then base model is ready, then I can do many various things. And this model is so powerful that this can be used to simulate thermal energy storage, something like around 600 degrees centigrade, 700 degrees centigrade, where radiation is a big issue. So means just I have to incorporate some source term, and this model will start working on that. Even this model is equally applicable to various applications also. So we have done our validation for different cases. Unfortunately, at 400 to 600 level, there is no experiments for our phase change based material. So currently we are doing that, but for rock based system, pebble based system, we have already shown that our model works good. So way forward is that we want to develop some new efficient method as well as new physics based model which will capture the flow, capture the performance of this storage maybe within 5%, 10% of the experimental results. And as we are going for high temperature, we are also developing new encapsulating material which can withstand that temperature. So along with my colleagues in chemistry department. So thank you. And I also thank various funding agencies, Sirius, DST, and particularly IRCC, IIT Bombay for giving me some fund to develop this experimental setup. And I also thank previous Dean R&D, Professor Balaji, for supporting me in this research. Thank you. And also these are my students actually who developed this model and experimental setup. Thank you.